And in the math lab, we look at something called Pascal's Triangle, which is a triangle of numbers full of patterns. Your job to start off with is to look at the triangle of patterns and see if you can fill in those 4 boxes. And if you think you've seen the pattern, see if you can write out all of row 8, or at least part of row 8, as much as you can. Did you notice the pattern and come up with a 5 here? How many people use this pattern? 1, 2, 3, 4, 6. Did you use that one? No? You didn't see that one? 1, 2, 3, 4, 5, 6 along the diagonal? What pattern did you see?
Just add the 2 up.
Just add the 2 up, which is really cool for this one, right? If you'd have the 2 above it, 5 and 10 make 15. 5 and 10, that makes 15. That's really helpful. Did anybody find the 15 in a different way? Did anybody do the diagonal again?
Yeah.
And you went plus 2, plus 3,
Yeah.
plus 4, plus 5. That's kind of cool. All right. And then probably the easiest way is the idea of adding the 2 previous ones. They all start with a 1, which technically is 1 plus there's nothing here, 0. The second one, 1 plus 6, 7. 6 plus 15, 21. 15 plus 25, 35. 20 plus 15, 35. 15 plus 6, 21. 6 plus 1, 7. And then another 1. Okay. Okay, now I'm going to get off topic just a little bit and just show you some of the cool things that happen. I mean, this 1, 3, 6, 10, 15, 21 are technically called the triangle numbers because the first triangle number is just a dot and you imagine it looks like a triangle. Then the second triangle number is you add 2 dots on the bottom, makes a triangle. Then you add 3 dots on the bottom. And if you counted the number of dots, this one has 1 dot, this one has 3 dots, this one has 6 dots. If I do the next one, it has 10 dots, and that is that diagonal right there, sometimes called the triangle numbers. What's neat about the triangle numbers is they are also just adding up numbers. This one is 1, this one's 1 plus 2, this is 1 plus 2 plus 3, this is 1 plus 2 plus 3 plus 4. Kind of cool that way. Okay, pattern number 1. Erase it. Go. In Canada, I call this the hockey stick identity. If you've never played hockey, I would call this the sock identity, which means if you start, I can start from this one, if you start from any edge, either left side or the right side, and you start drawing a hockey stick, and you can make it as long as you like or as short as you like, then all the numbers in the shaft of the stick, 1 plus 3 plus 6 plus 10 plus 15, will equal the number in the blade of the stick every single time. Doesn't matter, like, if I draw this mini stick, because everybody likes playing mini sticks, right? 1 plus 2 plus 3, 6 plus 4 is 10. It works. So you can draw little hockey sticks anywhere, as long as you can make the hockey stick as long as you want, and add up all the numbers in the shaft of that stick. It's going to equal the number in the tip of the blade, which is kind of crazy. Next crazy pattern. If we decided to add up the numbers in every row, well, this is pretty easy. Row number 1 adds up to 1. 1 plus 1, row 2 is 2. 1 plus 2, this is 4. And then this one is 8. And then this one adds up to... Anybody guess what the next one's going to add up to without adding it up? 32, you're right. And the next one? 64. And then 128. What is special about those numbers? Yes, they're doubling, but they're also considered, what are they? Powers of 2. This one is 2 to the 1, 2 squared, 2 cubed, 2 to the 4, 2 to the 5, 2 to the 6, 2 to the 7. That's kind of crazy. Then, I mean, there's obviously you draw a line down the middle. there's symmetry on both sides. Okay, so that's kind of cool as well. I'm gonna erase my hockey sticks just temporarily, maybe. No, I erased the whole page. That was a mistake. I want to just erase the hockey stick. Yes. Next, if we just like, instead of think of these as individual numbers, we think of each row as a big number. We would have 1, 11, 121, 1,331, 14,641. This might be a little harder for you to recognize, but those are special numbers too. What do they all have in common?
Are these prime numbers?
They're not prime numbers because 120, 11 is prime, but 121 is what times what?
11 times 11.
11 times
Or the
11.
powers of 11.
They are the powers of 11. If you go to your calculator and you type in 11 cubed, it's equal to 1,331. If you type in 11 to the 4, it's equal to 14,641. And 11 to the 5 is kind of weird because you don't normally have tens in numbers, right? So look at this, 11 to the 5. I'm going to have a 1. I'm going to have a 5. I'm going to have a 0, and the 1's going to carry over, make this 11. Then the 1's going to carry over, make this a 6. And if you try 11 to the 5, it's 161,051. Perfectly. Crazy. There's a lot of crazy patterns in Pascal's triangle. Pascal was a mathematician. Decided just to add the two previous number, make this triangle, and it all of a sudden craziness happened and it got named after him. The other day I put numbers in a square, nothing crazy happened. They're not going to name it after me. I tried. Okay. Next. If. Oh, like, so we got powers of 2, we got powers of 11. Take out straight line here. I'm going to make my straight line as best as I can on this. Yeah, I like that one. If I take that straight line and I drag it down until it hits a number. Oops, I don't want to drag all that. I just want to drag it down. Hey, I hit the number 1. Beautiful. Time to do it again until I hit the next number. Next, I hit the number 1. Oh, that's cool. Seems kind of dumb, right? What am I going to hit it next? Oh, next I hit both that one and that one. What do I hit next? Oh my goodness. Oh, I hit the 1 and the 2. Tell me when you see what I'm hitting.
Is it the golden ratio?
It's a golden ratio. Hey, 1 plus 3 plus 5. What the heck? Oh my goodness. 1 plus 3 plus 4. 8? Those are the Fibonacci numbers. That's messed up. If you keep going on that diagonal, you hit all the Fibonacci numbers. All the way through. Which is like, did they know that was going to happen? That's messed up as well. The next one would hit the 1, the 5, the 6, and the 1 adds up to 13. Do you know the Fibonacci numbers?
No.
The Fibonacci numbers are famous because you find the next one by adding the 2 previous ones. So 3 plus 5 is 8. 5 plus 8, the next one is 13. Oh, and have you really never heard of Fibonacci numbers? Never heard of the golden ratio? Do I really have to get off topic?
Mr. Chair, I love the Fibonacci sequence.
The Fibonacci sequence is so it's so cool. Okay, so
It's everywhere in nature.
yeah, so
It's awesome.
this is what. When Fibonacci, another maybe not so famous mathematician, came up with the Fibonacci numbers, and it is a set of numbers to represent a idealistic, well, not ideal, I don't know if that's the right word, but what happens to rabbits when rabbits reproduce, and we're not worried about rabbits ever dying, and we're also not worried about any incestuous rabbit relationships. Okay, so as long as we're clear on that, this is how Fibonacci's numbers started. Fibonacci says you can have baby rabbits and you can have adult rabbits. And you always have rabbits in pairs. So you start off with a set of baby rabbits, one boy, one girl. The next generation, they're no longer babies. They are now adult rabbits. The next generation, they are still adults because they don't die, but because they're adults, they have a pair of baby rabbits, another boy and girl. And rabbits are rabbits, so whenever they're adults, the next generation, they're going to have another pair of babies. So these adults, the next time, have another pair of babies, and these babies become adults, so now you have 2 adults and 1 baby, for 3 total. The next year, these 2 adults both have pairs of rabbits, and these ones become older. You have 5 pairs of rabbits. And if you do this all the way along, you get the Fibonacci numbers, which seems like, okay, somebody came up with this hypothetical rabbit situation. This should have gone away in history. But then these numbers started showing up everywhere. In fact, if you take 2 consecutive of these numbers and divide them, so like for example, 8 divided by 5 is 1.6, and then if I do 13 divided by 8, I get 1.625. And if I keep going with this, I get closer and closer to what is considered the golden ratio, which is sometimes
Can you draw it?
represented by the golden ratio, Greek letter phi, I'm not sure. And it's equal to 1 plus the square root of 5 divided by 2. Which also doesn't seem crazy, except it started showing up everywhere. So the Fibonacci numbers started showing up everywhere. A couple places they show up. Shouldn't be getting this off topic, but when a plant grows, it comes out of the ground as a weak little baby stem. And then it gets some more sunlight and it gets stronger and grows into a strong stem. And once it grows into a strong stem, what happens to a plant? It branches out into a weak one, and the strong one keeps going. The next generation, the strong one keeps going, branches off another weak one, the weak one becomes strong. Next generation, this one's strong, so it branches off, this one becomes strong, and this one branches off again. And they found out this is like how plants tend to grow. And this comes up all over with plants. Like flowers, if you count how many petals a flower has, there are flowers with 5 petals. There are flowers that have 8. There are flowers that have 13. The big flower, the sunflower, if you look at the seeds of a sunflower, they kind of spiral. And you can see a spiral sort of this way, and you can kind of see a spiral this way. And if you count the seeds in the end of the spiral, you'll get one Fibonacci number in one spiral, and the next Fibonacci number in another spiral. It's like messed up. So like, is this happening all over in nature? Yes. Check this out. If I start with a square that's 1 by 1, and then I draw another square that's 1 by 1, then I draw a square that's off of that 2 by 2, and then off this side I can draw 3 by 3. Off this side I can now draw a 5 by 5. If I start in the corner and draw a curve through each of the corners, you've got the shape of a snail and how a snail grows. It's messed up. And if you take this ratio of 8 to 5 and you actually draw a rectangle with that ratio, this is called the golden rectangle. And they've done studies with people that have no idea what's going on. They say, here's a bunch of rectangles. Which one's your favorite? And people will automatically, like, I don't know, but statistics will show people will be like, this one looks the nicest. And did the Greeks know this and have this number? Or is it just coincidence that the Greek Parthenon has these dimensions and was considered one of the ancient wonders of the world for being the most beautiful structured buildings that existed. Did they know that number? Or did they just feel that number? Did they just see it and say, this looks good? Okay? And now, like lots of things that we use in our life are built on this. Like cereal boxes that are in the shape of the golden rectangle, you're more likely to buy that. Have you ever seen a cereal box that's a perfect square? You'd be like, ooh, I don't want to buy that kind. Right? Credit cards. Oh, they want you to spend money. Like, I love this rectangle. I just want to spend, I want to hold it all the time and spend lots of money. This is all embedded in stuff. Even in music, like Beethoven's, is it the 5th or the 9th?
I think it's the 5th, because it's like a time signature.
Right? It's the one that goes bum 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 bum, like, and keeps going like that. So Beethoven introduces his main theme in bar number 1, bum 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 bum, and then he plays around with it, I think, for like 233 bars or measures, which is a Fibonacci number. And then he reintroduces it for the first time again, and then uses the previous Fibonacci number to finish it. And that spacing has the nice breakup of one space to another. So did he do that on purpose to make it sound the best, or did it just sound the best to him and it was coincidence? Crazy. Okay, those are Fibonacci numbers. We got way off topic. We're talking about Pascal's Triangle. Not as famous as Fibonacci numbers, but Fibonacci numbers show up. Okay? And then in this, if you kept on going and decided that wherever there was an even number, you drew a triangle and shaded it in. Oh, here is, a bunch of even numbers, and then there's one here. And you did that, and you kept going, you would make Sierpinski's triangle. Oh, now I have to show you something about Sierpinski's triangle. Oh, I shouldn't have made a video. Everybody who watches it just going to think that I just go off topic all the time. Here we go. Let's see what. All right, so I got a student to make this for me in computer science. All right, we'll go fast. We'll do the fast version. Or maybe I have, wait a minute. Let's go back one.
Much different colors.
Sierpinski triangle, final, multicolor, white, not really random. Let's see what the final one. Let's open this up. Oh, I've got fast version here and slow version. We'll turn off some lights.
Is it a fractal?
It is a fractal.
Oh, genius.
Okay, here we go. What color do you want to see it?
I would like to see a cyan fractal.
Cyan version. Here we go. Hit start. Woo! Okay, and what is crazy about this is that the program for this is simple. Well, let's remind myself of that later. I've got 3 corners of an equilateral triangle. I told the computer to randomly pick a dot anywhere on the screen. It's like, okay, maybe I picked, if I were to guess this was the first dot, I could actually tell. This is the random dot that got started down here in the bottom. Then I say, okay, computer, randomly pick one of the 3 corners. It's like, okay, I'll pick top corner. Okay, whichever one it picks, it then draws a dot halfway there. So it drew this dot second. Then I said, pick a random one again. It actually picked the same one again, went here. Pick a random one. Then it went here. Pick it again, random here, then here. And then it probably picks something inside. Once it gets in inside the triangle, it never gets out. and it keeps picking random corners and always moving halfway. And no matter where, that's the simple rule. Pick a corner, draw a dot halfway, and no matter where it starts and what it does, it draws the same thing every single time. No matter where it randomly picks and no matter how it randomly picks a corner, it makes the same shape every single time, which is an idea of fractals, is a simple rule with randomness involved, and yet it makes the same thing every time. And biologists wonder if there's some of this built into how DNA and like, how is it that a little tiny seed, right, you plant it and you don't get a monkey. You always get the same plant. Tomato seed always makes a tomato. Like I've never planted a tomato seed and got a monkey or a hippopotamus or anything. So I can pick, right? This is what this program does every single time. What color do you want this time?
Red.
Red. Picks a random point. Looks like, right? Anytime you see a point in the black parts, that was one of the beginning points. Here, probably this was their first point. Then it went halfway, got there. And then made the triangle every single time. And the crazy thing is if you zoomed into this,
Keep going.
It goes on.
it would keep going on, zooming in finer and finer and finer. You'd get the same shape over little tiny triangles, no matter how far you zoomed in. It's insane. And yet, simple rule, right? Pick a random point. Always measure halfway. Do this forever. And you make the same shape every single time. Messed. Oh, wrong, Michael, sorry. That was a little brighter than I hoped. Crazy. Okay. Done. So Pascal's triangle also has Sierpinski's triangle. Now, why are we doing it? How does this relate to combinations? Turn the page. If you did 4 choose 0, 4 choose 1, 4 choose 2, 4 choose 3, 4 choose 4 on your calculator, you would get 1, 4, 6, 4, 1. You get a row of Pascal's triangle. So Pascal's triangle is also combinations. This is like math has stuff in it that's like, what? How does this all happen? Oh, more like golden ratio is so much built into the human body as well. One last thing, okay? So like if you take your joints of your fingers and you divide them, you will get very close to the 1.6 golden ratio. If you take your height divided by up to your belly button, you'll get very close to 1.6. If it's way off, you look funny. I'm sorry, but you have like when someone says, "Oh, that person is disproportionate," they got long and then tiny little legs, right? It's just like something's not quite matching up. But generally, that measurement from here to here, and you divide them, you'll get close to 1.6. Your lengths of your fingers. Like, it shows up all over the place, which is kind of messed up. So we can fill in these combination files. Row 1, 0, choose 0. 1 choose 0, 1 choose 1. Then 2 choose 0, 2 choose 1, 2 choose 2. 3 choose 0, 3 choose 1, 3 choose 2, 3 choose 3. 4 choose 0, 4 choose 1, 4 choose 2, 4 choose 3, 4 choose 4. And now we're going to make this connect to algebra. The way that this connects to algebra is You already know how to, I'm gonna start a new page here. You can write this down if you want. You can put it on the side of page 736. Oh, wait, you know what? It is actually connected to the construct the understanding of 8.6. So we'll do that. We'll do this intro video of 8.6 as well. There we go. Wait for it. Yeah, so turn to page 738. And we have all these things that Pascal's Triangle is doing already. All those patterns, none of which we're going to use, except for the combinations part. Ooh, this looks like 11, choose 0, 11. I always use the second number of Pascal's triangle to figure out which combinations it is. If the second number is 11, well, you know it's 11, choose 1. So this one will be 11, choose 0, 11, choose 2, 11, choose 3, 11, choose 4, 11, choose 5. And it has 12 things in there, so that's going to be row number 12, because row number 1 had 1. So that's how I would be able to write the fifth term. 3, 4, 5. This one will be 11, choose 4 in NCR notation. Okay, but what I wanted to show you was this kind of crazy thing that happens here. Well, x plus y to the 0. Anything to the 0 is?
0.
Oh, 1. Oh, that one's way too big. I'll just write a nice little. I'm going to do it. It might be a little weird for you. I'm going to put it way over there. We'll see why in a second. X plus y to the 1 is just x plus y, which you don't have to, but you could write a 1 there. 1x plus 1y. You know how to multiply things out. You've squared lots of things this year, right? You'd have to FOIL it out, do all the arrows. You would get x squared plus 2xy plus y. And of course you don't need to, but there could be a 1 there, a 1 there. Oh my goodness. You already see what's happening. I can see that you see what's happening. This is crazy, I know. X plus y cubed would be a little annoying to do. Because you would have to do x plus y times x plus y and get the answer that you had there. And then you have to take all of that and multiply it by another x plus y. And you get the following. You get an x cubed. Makes sense that the x times the x times the x, when you write them all out, would give you an x cubed. And then you're going to get 3. After you do all the things and combine your like terms, you're going to get 3 x squared y's. And then you're going to get 3 xy squareds. And finally, you're going to get a y cubed, which you don't need these ones there, but they're kind of cool if they're there because you start seeing something. And if you notice the pattern, because there's also a pattern happening with the exponents, we should be able to do x plus y. I don't know what's happening there. Oh, there we go. X plus y to the 4. Do you see the pattern in the blue numbers? So I might just want to start with 1, 4, 6, 4, 1. I know that that's going to be my next set of blue numbers. Now what's going to go with the 1? What do you think?
1 or x to the 4.
X to the 4th. Excellent. Plus, what's going to go with the 4?
4x cubed.
4x cubed y, nice. What's going to go with the 6?
So 6y, 2.
X squared what?
X squared y squared. And then with the next 4? It's y cubed. And finally, y to the 4. So a little explanation of what's happening here and why this works, explained with combinations. X plus y to the 4 really means x plus y times x plus y times x plus y times x plus y. Whew. And if you drew arrows, this x goes to there, this x goes to there, this goes to there, this goes to there. Then with whatever you get, there would be arrows going all the way through. So if you consider all of the possible arrows going through, one of them would look like this. Hop to the x, hop to the x, hop to the x. And if I did all the x's multiplied by each other, there would be x to the 4. Okay? I'm going to go in orange now. I'm going to take away these previous arrows so that. Took away the previous arrows. Can you tell me a way that I could get, we're going to do this one in orange. I want 1y. I have to either start with the x or y. Where should I start? Pick one.
Start with what?
You're going to start with a y? Well, if you only want one y, in this one you can't hop to the other y. You'd have to hop to the x. Then you'd have to hop to this x. Then you'd have to hop to this x. That would give me 1y and 3 x's. Is there any other way I could start in this one and still get 1y?
Yeah.
What would I do? Start with the x?
Yep.
Where do you want me to hop to?
Another X.
The other x, okay. And then?
Another X.
Another x. And then?
And then the Y.
And then the y. Good. Is there any other possibilities? Yes. What should I start with?
X.
I start with the x, okay. And then hop to?
Y.
Hop to the y. Well, then I need to go to the x.
X.
And then the x. Any other ways?
Yep.
Yes, where?
Start with X.
Start with the x.
Go to the X again.
Go to the x again.
And then go to the Y.
And then go to the y. And then go to the x. Is there any more?
Yep.
Which one?
Start with Y.
Start with the y? Oh, I did that already. And then
Oh
X-
yeah, never mind.
and it's on the top.
Yeah.
How many different ways did we count? 4 ways to do that. Combinations wise, this 4 is for choose 1. What did we choose in each path? We chose 1y. And the other ones had to be x's. In these paths, you're choosing 2 y's. Here, choosing 3 y's. Here, choosing all 4 y's. Here, for choose 0, choosing no y's. Only one way to do that, always pick the x. And there your combinations comes through with the binomial theorem. Notice that when it's x to the 4, that the exponents always add up to 4 in each one. Because you're always choosing something from each bracket. I have 4 brackets, I'm choosing either the x or the y, all the way through. So my exponents will always add up. We write it in descending order from like x4, x3, x2, x1, x0. But you don't write the x0. But this allows us to find a shortcut for figuring these values out. Awesome. And they have this demonstrated here On the next page, same thing we discovered with Pascal's triangle. So Pascal's triangle gets us the numbers in front, and then the pattern tells us about the exponents.